This video is designed to help you understand how you can use the ideas of parabolas to, for example, find the flight or arc of a cannonball, time spent in the air, something like that. Any kind of thrown or flying object. One thing to kind of keep in mind is that this entire analysis ignores air resistance. So ignoring air resistance, because that at these kinds of speeds is a significant factor. So that's higher level math, not appropriate for an algebra course, but at least this analysis is the first order analysis, and then if you're throwing a ball or something that's not moving terribly fast, air resistance is not a big deal and can be reasonably accurate, but certainly over longer distances and cannonballs and rockets and things like that, air resistance is important. So just keep that in mind, that this is an exercise in understanding the algebra here. If you have a cannon that's sitting on the ground and you need to shoot the cannonball and try to hit a castle that's 1,500 feet up in the air, or up on a nearby mountaintop 1,500 feet, we can do the analysis to figure out several things. We can figure out how long it will be flying, what the highest or maximum height that the cannonball will reach, and also how far away from the castle the cannon should be positioned. Now, I've given you an initial velocity split into the two vectors of the upward velocity and the horizontal velocity. You can do a little other math, Pythagorean theorem or special right triangles or trigonometry. If I tell you an initial velocity of the cannon directly out of its mouth in the direction it's going, you can split it up into its two vectors yourself using right triangle calculations. In any case, on this one, just for simplification, I'm giving you an upward velocity of 500 feet per second and a horizontal velocity of 300 feet per second. The horizontal velocity will be constant throughout the flight as gravity is not slowing it down. Obviously, air resistance would, but the upward velocity, of course, is counteracted by gravity. The equation that one would write relative to this, the height at any time is equal to the downward force of gravity. That's the acceleration of gravity, plus the initial upward velocity times time, plus the initial height times time. I'm going to add that component in just so you're aware of it. At this point, I'm suggesting that the cannon would be resting on ground level. So here's the ground down here. So if it's at level 0, h of I in this case is going to be 0. So this is the general equation, and it tells us the height of the cannonball at any given time. If you put in t as 0 before, just at the time you fire off the cannonball, you'll see that the height would be 0. And of course, we can plug in any other time we want. We could plug in 2 seconds, and just to see what the height of the cannonball is going to be during that time. At that time. However, what we're interested in is when is the cannonball at 1,500 feet? In other words, crashing down on our castle. So what we're actually going to do is solve this quadratic equation. And what that means is we want to solve it using either factoring, or since it doesn't factor nicely, we'll use the quadratic formula, but we'll need to set it up for that. So we'll see that in the next slide. So here's the equation we finished with on the previous slide, and to sort this out most easily, I would actually add 16t squared to both sides and subtract 500t from both sides, getting us the following equation: 16t squared minus 500t plus 1,500 equals 0. It's also possible, that's a pretty lousy 0, equals 0. It's also possible to subtract 1,500 from both sides, and then just to clear the negative sign in the first coefficient, which is not necessary, but the coefficient of t squared, it's nice to have that be positive. I think this is a little cleaner way to do it. In any case, if you use the quadratic formula, there's no issue with where the signs are, as long as you're careful with plugging the signs into your equation. So what this is really saying now, we're solving for the t or the t's when this equation is true. I'm going to write it as x, because most people are used to seeing that. Well, actually, I'll just write it as t. It's going to be t equals the opposite of b, which is 500, but it's the opposite of negative 500, so we're going to call it plus 500, plus or minus, and that's going to give us the 2 times 500 squared, b squared, so we're actually squaring negative 500, but when you square a negative number, it's also positive, so we can simply write 500 squared, minus 4ac. So this is going to be minus 4 times 16 times 1,500. Okay? So this is all over 2a, which is 2 times 16, or 32. Now, we need to sort this out, so this is where you grab your calculator and do a little work. If you sort out what's in the square root sign, you're going to get 154,000 over 32, and that means that your answers are going to be approximately 500 plus or minus, and the square root of 154,000 is 392.4-ish. So I'm going to write 392.43, I guess, over 32. So this gives us 2 times 500 minus 394 divided by 32 is approximately 3.36 seconds. And 500 plus 394.43 divided by 32 is approximately 27.89 seconds. So keep in mind also that 500 over 32, which is the time in the middle of this, well, it's the center line of the parabola. We'll come back to that in just a minute. That number is going to be a useful number we'll talk about in the next slide, but that is approximately 15 points, is actually exactly 15.625. So let's see on the next slide what all this means. I'll make ourselves a little diagram again, okay? But at any rate, what we found are 2 times, 3.36 seconds and 27.89 seconds, which are the solutions to the equation, when is this cannonball 1,500 feet in the air? So let's take a quick look and see what that means. So here we have another drawing of the situation, the cannonball firing it off at t equals 0 seconds. So if you think about this axis as time and this axis as height, what we're actually seeing is at the height of 1,500 feet, the cannonball obviously passes 1,500 feet on the way up, and that must be at 3.3 seconds. 3.36 seconds. Okay? And it again passes the cannonball, passes through the height of 1,500 feet at the following time, 27.89 seconds. So obviously, if you're interested in hitting a bird on the way up, you might have hit it in 3.36 seconds of flying. But if you're hitting the castle on the way down, it's going to take 27.89 seconds roughly. This actually graphically is a parabola. Obviously at t equals 0 seconds, and this is nothing in here is drawn to scale or whatever, it's just a quick sketch. But at 0 seconds, we're at ground level essentially, assuming the cannon is basically at ground level. Maybe it's a few feet high, but who cares? If you view this as the parabola, the vertex or center line of this parabola must happen an equidistant from these two times. And if you go back to the previous page, what you're going to find is that it's the center line plus or minus some number of seconds. So that center line is at that 500 over 32 seconds. This is 500 over 32, or approximately 15.625 seconds. So what we know is that the cannonball will hit the castle 27.89 seconds after it's launched, again, ignoring all the air resistance and so forth. But if we wanted to find out how high the cannonball would be, remember we have an equation for the height of the cannonball at any given time, and now we have a time where it's at its apex or vertex. Since this is a parabola, the vertex there is the point that we're interested in. So the vertex is clearly going to be found by plugging back into the height equation. So what we're actually finding is the height at 15.625 seconds is negative 16 times 15.625 squared, that's the negative 15t squared, plus 500t. And 500 times 15.625. So if you actually calculate that number, so let's erase that t there and clean that up, sorry about that. 15.625. So when we actually do this calculation, you'll find that this gives you roughly 3,906.25 feet. Of course, any decimals here are suspicious because of air resistance and so forth. In fact, it's probably not going to be anywhere near 3,906 feet. But assuming this was done in a vacuum and we had sort of normal Earth gravity, we would have a peak height of 3,906 feet if you run that calculation. So this is 3,906 feet, and I'll put the 0.25 just for fun. Now, the other question is, how far away should you position the cannon? And that has to do with what the horizontal velocity is. And so the distance away, since it's flying for 27.89 seconds, let me write distance away, and I'll write horizontal distance away, because that's actually asking how far away should the cannon be positioned in order to shoot this arc, okay, and strike the castle. And that's just a simple distance equals rate times time equation. Distance away is going to be whatever the horizontal speed was, which I think was 300 feet per second, but let's write r sub h for horizontal, or r sub horiz, times the time it spent flying. And of course that gives us 300 feet per second, and let's actually put the units in here, feet per second, times 27.89 seconds. And that winds up being approximately 8,367 feet. So what it means is you should position the cannon, assuming that all of this was, again, without air resistance, you should position the cannon approximately 8,367 feet away. In 3.36 seconds, it will pass up on the upward direction, pass through 1,500 feet. In 15.625 seconds after firing, it will reach the apex or peak height of 3,906 feet. And on the way down, it will crash into the castle at 1,500 feet high in 27.89 seconds after firing. I hope this has made things as clear as possible. Thank you.